Okay, we're doing a vector intro video here. Okay, so this is a video about vectors, and I'm going to cover some stuff we learned in class in the strand, or the expectation C1, which is just about representing vectors. So we learned what a vector was today. So we talked about vectors have a magnitude and a direction, whereas a scalar quantity just has a magnitude and no direction. Okay, so if we wanted to draw a vector, we can draw it as a geometric vector or an algebraic or Cartesian vector. So for example, let's say we wanted to represent something like a vector that was 5 kilometers, maybe north, 20 degrees east. So we just want to represent this as a geometric vector. So we always do north pointing up like that, east, south, and west. So if we're going north first, and then we go 20 degrees towards the east, it's going to look like a vector that looks like this. So this would be 20 degrees. This down here would be 70, because we know that's going to add to 90, just if we wanted to know. And then we know the length of this vector is 5 kilometers. That's the magnitude. Okay, so that's how we could draw a vector, and that would be kind of like a geometric vector. And then we also talked in class today about algebraic vectors. So algebraic vectors are when you stick them on kind of a Cartesian plane and you separate them into their x and y components. So if we wanted to turn that one into an algebraic vector, so we know this is 5 kilometers long. So we want to figure out what are the x and y components of this vector. So let's say I name this vector v. Then I could say this is the x component, like make a little subscript x, and this is the y component, so make a little subscript y. So I split it into my x and y components, and 5 here is the magnitude of the vector. Now I know that this angle in here is 70 degrees, so I'm going to use that to help me. So basically, to find the x component, I'm going to use cos, because I know that, just to remind you, cos theta is equal to the adjacent side over the hypotenuse. So if we're just going to find x, this is my adjacent side and this is my hypotenuse, if in reference to this 70-degree angle here. So my x component of my vector would be, well, actually, before I write it like that, let me write it like this. Cos theta, bleh, redo. Cos 70, I know the angle is 70, is equal to adjacent over hypotenuse. So the x component of my vector over 5. And then if I want to isolate my x component here, we'll just multiply both sides by 5. So there we have it, 5 cos 70. So this is the x component. And if I had a calculator, which I don't, you could actually figure out that answer. Okay, and then if I wanted to find my y component over here, that's opposite to my angle. So I'm going to use sine. So sine 70 degrees is equal to my y component divided by 5. So opposite over hypotenuse. And then if I just want to isolate my y component, 5 times sine 70. And you can punch that into your calculator, figure out the answer, but I just don't know. Did not bring my calculator. Okay, so now if I wanted to write that as an algebraic vector, let's call it vector v, I would describe it as a set of coordinates. So I'd write my x coordinate, which is 5 cos 70. Sorry, again, I don't know what that is. And then my y component, which is 5 sine 70. But it's not horrible writing it like that anyways, because then I haven't rounded anything, you know? Like, what if it equals like 2.7134? I don't know. Like it might be nicer leaving it like this. These would be the exact values. So how we write geometric vectors is we actually write the magnitude of the vector, so 5, and then we write the direction. How we write an algebraic vector, we don't have a direction. Well, we do. It's on the Cartesian plane. So we don't have to write like north 20 degrees east or north, yeah, whatever. We just have to write it like this. And that gives us a magnitude, which is still 5, and a direction, because it's always situated at the origin, and it basically refers to this end point here. That's what the x and y coordinate refer to. So that's how they look differently. So let me just give you a different example. But a geometric vector would look like this. 10 kilometers per hour, traveling south 20 degrees west, for example. Whereas, boom, an algebraic vector could just look like this. Vector V is 1, 3. And that gives you a magnitude and a direction. Now, let's say we didn't know, we want to find the magnitude. Well, in our geometric vector, the magnitude is just 10. And there's our direction. Boom. But in an algebraic vector, we can't tell the magnitude right off the bat. We just know the location, of it on a Cartesian plane. So if I actually sketched out where would like 1 and 3 happen, right here, I attach it to the origin, that's what my vector looks like. And then if I actually wanted to figure out what the heck is the magnitude of my vector, remember we put it in absolute value signs, we can actually find the magnitude of the vector. Because we know that this x component is just 1. We know the y component is 3. That's a 90-degree triangle. Why don't we just do Pythagorean theorem? Basically, 1 squared plus 3 squared, which is 10, I think. 3 squared is 9, 1 squared is 1, 9 plus 1 is 10. So now we know the magnitude of vector v is the square root of 10. So if I wanted to write it as a geometric vector, let's say I'm like, oh, algebraic sucks. I want a geometric vector. I can actually write this vector here, 1, 3, as a geometric vector by saying, okay, I know it's going to be root 10. Sorry, again, I don't have a calculator, so I'm just going to leave it as root 10. I know that's what the length is. Now I just need a direction. So I need to know, like, this angle in here would be cool. Sorry, I drew that so small. So I'm thinking I might just use, so that's my magnitude. I might just do tan. So if I wanted to find that angle, I might as well just do inverse tan of opposite over adjacent. No idea what that is. Do I have a calculator? Let's just check. Intermission. I'm back. I do have a calculator. Okay, inverse tan of 3 is 72. 72 degrees. Okay, so now I know. Let's just draw this again. I got this vector here. Boom. It's a little bit inaccurately drawn. I know my x and y components are 1 and 3. I found the magnitude is 10. And I just found the angle 72. And therefore, I would know that top angle is 90 minus 72, which is 18 degrees up here. So if I wanted to write this algebraic vector, 1, 3, as a geometric vector, I could say vector v is also equal to the square root of 10, and it's traveling north 18 degrees east. Boom, now it's geometric. So I just took an algebraic vector and turned it geometric. And above, I showed you how to turn a geometric vector, like this guy, into an algebraic vector. So now you guys know how to turn algebraic and geometric vectors into each other. And you know how to represent them. So you should also know how to do stuff like this. Like if I said, draw this vector. Someone's traveling 100 kilometers per hour at a bearing of 160 degrees. So you know, oh, bearings are always given from north. That'd be 90, that'd be 180, so it's like 20 less than 180. So you know that would be 160, this would be 20, this would be 100 kilometers per hour. Cool, so you can draw that vector. Good job. And you could also draw vectors that are like, what about someone traveling 50 kilometers in south 23 degrees west? No problem. South. Never eat shredded wheat. And then you're just going south 23 degrees towards the west. So this would be 23 degrees. The length of this line here would be 50 kilometers. Boom, you just drew it. Okay, so to sum up, we know what algebraic and geometric vectors are. We know how to draw vectors. We know what a vector is. And I think that's about it. Oh, we can find the magnitude of vectors too. And that, well, sometimes it's just given to you. But also you can use the Pythagorean theorem to find magnitude of vectors, like algebraic vectors. So we can do a lot. So that is the end of my video.